Welcome to Midnight Science. Tonight we drift toward the farthest edge of time, to the quiet question of how everything finally ends. Not with fear, but with wonder. We will visit the theories scientists whisper about in the language of cold equations and dying stars, and we will gently ask which ending the universe seems to prefer. If this journey brings you rest, a soft like and a subscribe helps others find this place when they cannot sleep. Before we begin, settle in, breathe slowly, and let your shoulders sink. Tell me softly in the comments where you are listening from and what hour glows on your clock tonight. There is something tender about the idea of an ending. Not a sudden ending, not a violent one, but the kind of ending that arrives the way evening arrives, slowly, patiently, almost without anyone noticing. Tonight we are going to sit with that idea for a while. We are going to think about the ending of everything, and we are going to do it gently, the way you might think about a long journey that is still very far away. The universe, the one that holds you now, the one that holds this room and this hour and the quiet sound of your own breathing, is not a fixed thing. It is not a painting hung on a wall. It is more like a vast, slow breath, drawn in across billions of years, still being drawn, still expanding outward into a darkness so wide that even light grows tired crossing it. Everything you have ever seen, every star in every photograph, every galaxy spiraling in the deep, is part of that breath. And like every breath, it has a shape. It began somewhere. It is moving through time. And somewhere far ahead of us, in a quietness we can barely imagine, it will reach its furthest point. This is not a thought meant to frighten you. It is a thought meant to soften you. Because the ending of the universe is not something that will happen tomorrow, or next year, or in any year that will ever appear on any calendar humans will ever write. It will not happen in the lifetime of your children, or your children's children, or the species that comes after them, or the species after that. The ending of the universe lives on a scale so distant that even imagining it becomes a kind of meditation. And tonight, we are going to imagine it together, slowly, with care, the way you would turn a small stone over in your hand to see all of its sides. For most of human history, no one believed the universe could end. The sky overhead seemed permanent, unchanging, eternal. The stars that watched over the first cities watched over the last ones too. The same constellations rose over Babylon and over Athens, and over the small wooden ships that crossed unknown seas. To the people who looked up, the heavens were the one thing that did not change. Everything on earth could be born and could die. Kingdoms could rise and fall. Rivers could shift their courses. But the stars stayed where they were. The sky was the great steady thing, and the world below was the restless thing. Ancient sky watchers built their lives around this stillness. In Mesopotamia, priests tracked the slow wandering of the planets and believed they were reading the will of unchanging gods. In Egypt, the pyramids were aligned with stars that seemed to promise an eternity beyond death. In China, court astronomers kept careful records of comets and eclipses, treating any change in the heavens as a rare and meaningful event. In the high mountains of the Andes, in the deserts of Australia, in the cold forests of the north, people watched the sky and gave names to its patterns. And in every one of those places, the underlying belief was the same. The cosmos was old, but it was not aging. It had always been here, and it always would be. Even the great philosophers of ancient Greece, who questioned almost everything, struggled to imagine a universe that could change in any deep way. Aristotle taught that the heavens were made of a different substance than the earth, a perfect material that could not decay. The stars were not born and they did not die, they simply were. This idea was so powerful that it lasted, in one form or another, for nearly 2,000 years. The cosmos was a kind of crystal sphere, polished and eternal, turning slowly above a small, restless world. It is gentle to remember how recently this belief began to soften. Just a few hundred years ago, when Galileo lifted a small telescope to the sky and saw the moons of Jupiter, the eternal sphere began to crack. Not loudly, not all at once, but in slow and careful ways. The moon turned out to have mountains, the same kind of mountains that exist on Earth. The sun turned out to have spots, dark patches that drifted across its face like weather. The planets turned out to be worlds, each one different, each one with its own quiet story. The sky was not made of perfect material after all. It was made of the same stuff as everything else. And once the heavens were made of the same stuff as the earth, a new possibility opened. If stars were objects, then perhaps they could be born. And if they could be born, then perhaps, somewhere far ahead, they could also fade. This was a thought so new that no one quite knew what to do with it. For a long time, people held on to the idea that the universe as a whole, even if its individual parts changed, must still be eternal. Stars might come and go, but the cosmos itself was forever. It had no beginning. It had no end. It simply held everything in its quiet hands. This belief lasted longer than you might think. Even into the early 20th century, even after Einstein had written down the equations that describe gravity and space and time, most scientists still assumed that the universe was, on the larger scale, a steady thing. Einstein himself believed this at first. When his own equations seemed to suggest that the universe might be expanding or contracting, he added a small term to keep it still. He called it the cosmological constant. He added it not because the math demanded it, but because his intuition did. The universe, he felt, must be the kind of thing that simply was. It must not be growing, it must not be aging. And then, very quietly, the sky began to speak again. In the 1920s, a young astronomer named Edwin Hubble was working at the Mount Wilson Observatory in California, looking through a telescope so large it could see things no human had ever seen before. He was studying distant smudges of light that some scientists believed were clouds inside our own galaxy, and others believed were entire other galaxies, immense and far away. Hubble proved that the second idea was correct. The smudges were galaxies, every one of them a great wheel of stars like our own, scattered across a vastness that had been hiding in plain sight. The universe, it turned out, was not just our Milky Way. It was hundreds of billions of galaxies, each one holding hundreds of billions of stars. The cosmos became, in a single decade, almost unimaginably larger than anyone had thought. But there was something stranger still. As Hubble studied the light coming from these distant galaxies, he noticed a pattern. The light was stretched. The color of every distant galaxy was shifted slightly toward the red end of the spectrum, as if the galaxy were moving away from us. And the further the galaxy was, the more its light was stretched, the faster it seemed to be moving away. It was as if the entire universe were quietly drifting outward, every galaxy receding from every other galaxy, like raisins inside a loaf of bread that is slowly rising in an oven. This was the discovery that changed everything. It is one of the most beautiful and quietly devastating ideas in the history of science. The universe is not still. The universe is moving. The universe is expanding. And if it is expanding now, then it must have been smaller yesterday, and smaller still the year before, and smaller still the century before that, and the millennium before that, and so on backward into the deep past, until you reach a moment when everything that exists was gathered together into a single point of unimaginable density and heat. The universe had a beginning. It had a moment when it started. And here is the thought that follows, the thought that has kept cosmologists awake for 100 years. If the universe had a beginning, then it is not eternal in the way ancient people imagined. It is not the unchanging crystal sphere. It is a process. It is a journey from one state to another. And if it began, then somewhere ahead of us In a future so distant it makes the past seem brief, it will also end. The same logic that gave the universe a birth gives it, in some form, a death, or a quiet transformation, or a slow fading, or something stranger still. Take a slow breath here. Let your shoulders soften. There is no urgency in this thought. The universe is 14 billion years old, give or take. And the kinds of endings we will talk about tonight are measured in numbers so large that 14 billion years feels like a single heartbeat inside them. We are not visiting a deadline. We are visiting a horizon. We are looking out across an unimaginable plane of time and asking, very quietly, what lies at the far edge? For the last century, this question has belonged to cosmologists. They are the scientists who study the universe as a whole, the way it began, the way it moves, the way it may one day finish. They use the largest telescopes ever built, the most sensitive instruments ever designed, and equations that stretch across pages. But underneath all of that machinery and mathematics, what they are really doing is something very old and very human. They are watching the sky. They are wondering what it means. They are asking the same questions the ancient sky watchers asked, only with new tools and a new vocabulary. And what they have found is that the ending of the universe is not a single story. It is several stories, several quiet possibilities, each one shaped by what we still do not fully understand. The fate of the cosmos depends on things that are still being measured, still being argued over, still being slowly uncovered. It depends on the behavior of a mysterious force called dark energy, which seems to be pushing everything apart. It depends on the geometry of space itself, on whether the universe is curved or flat. It depends on what matter really is, on what energy really is, on whether the laws of physics we know now will still hold a trillion years from now. There is something tender in this uncertainty. It means the ending is not yet written. It means that even now, in this quiet century, scientists are still listening to the universe, still gathering its faint signals, still trying to understand which of several beautiful endings is the one that will actually arrive. Each of these endings has a name. Each of them describes a different kind of farewell. And tonight, we are going to visit them one by one, the way you might walk slowly through a gallery of paintings, pausing at each one to see what it shows. The first ending is called the heat death. It is sometimes also called the big freeze. It is the slow, patient, almost gentle scenario in which the universe simply runs out of usable energy. Stars burn out one by one. Galaxies drift so far apart that they can no longer see each other. Black holes themselves slowly evaporate over spans of time so long that the numbers stop feeling like numbers. And at the end, what remains is a vast cold stillness, a universe so spread out and so quiet that nothing new can ever happen. This is the ending most scientists currently consider the most likely. It is not violent. It is not sudden. It is the cosmos slowly settling into rest. The second ending is called the Big Rip. It is a stranger and more dramatic scenario in which the force of dark energy grows stronger over time, pulling everything apart with greater and greater urgency. In this ending, the universe does not fade. It unravels. Galaxies are torn from one another, then galaxies themselves come apart, then solar systems, then planets, then molecules, then atoms, all the way down to the smallest pieces. It is an ending of unbinding, a returning of everything to its most basic elements. Whether this ending is real depends on whether dark energy stays steady or grows, and that is a question we still do not have a clear answer to. The third ending is called the Big Crunch. It is in many ways the opposite of the Big Rip. In this scenario, the expansion of the universe slows, stops, and reverses. Gravity wins. Galaxies that were once drifting apart begin to draw together. Space itself contracts. The cosmos falls back in on itself, growing hotter and denser until everything that exists is once again compressed into a single, unimaginable point. It is the ending that mirrors the beginning. It is the breath drawn out, then drawn back in. Once, this was considered the most natural ending for the universe to have. Today, the evidence makes it seem less likely, but it remains beautiful, and it remains possible. The fourth ending is more like a beginning. It is called the Big Bounce, and it is the idea that every ending of a universe is the start of another one. The cosmos contracts, reaches its smallest point, and then expands again, beginning a new cycle. In this view, the universe is not a single event, but a rhythm, a great cosmic breathing in and out across spans of time without end. Some versions of this idea suggest that there have been countless universes before ours, and there will be countless after. The universe never truly ends. It only changes form. It is a thought that carries something almost like comfort. And then there is a fifth possibility, stranger than all the others, hidden in the deep mathematics of the quantum world. It is sometimes called vacuum decay, and it suggests that the very fabric of empty space may not be in its lowest possible energy state. Somewhere, sometime, a tiny bubble of a deeper, more stable kind of space could form and begin to expand at the speed of light, rewriting the laws of physics as it spreads. It is the kind of ending that does not destroy the universe so much as transform it into something entirely new. It is rare, it is theoretical, but it is not impossible. These are the rooms we will walk through tonight. Heat death, the big rip, the big crunch, the big bounce, and the stranger possibilities at the edges of physics. We will not rush from one to the next. We will sit with each of them. We will let them be what they are, neither tragic nor triumphant, only deeply, quietly real. It is a strange thing to consider that the universe might have several possible endings, and we do not yet know which one will arrive. It is even stranger to consider that the answer may already be encoded in the night sky above us, in the faint light from distant galaxies, in the slow drift of expansion that began before the Earth was even formed. Somewhere in that light, somewhere in those measurements, the future of everything is quietly waiting to be read. We are still learning the language, we are still building the instruments, but each year we come a little closer to understanding. And here is something worth holding gently before we continue. The fact that the universe will, in some form, one day end, does not take anything away from this moment. It does not make the warmth of your breath less warm, or the quiet of this hour less quiet, or the soft weight of your body against the bed less real. If anything, the vast slow ending makes this moment more precious, more particular, more its own. You are a small living thing in a cosmos that is currently in its long, bright middle. The stars are still burning. The galaxies still hold together. The laws of physics still allow water and stone and music and dreams. All of the conditions that allowed you to exist are, for now, still here. That is the gift of cosmology. It does not bring the ending closer. It only widens the moment. It places you inside a story so vast that your own small place in it becomes a kind of miracle. You are made of atoms that were forged inside stars that lived and died billions of years before the Earth existed. You are walking around in the leftover light of those ancient deaths. And one day, billions of years from now, the atoms that currently make up your body will be scattered back into the universe, ready to become something else, ready to be part of whatever the cosmos becomes next. Tonight, we are going to visit the long arc of that story. We are going to walk through the slow ways the universe might end, the quiet and the strange, the gentle and the dramatic. We are going to do it without urgency, without alarm, the way you might walk through an old library, running your fingers along the spines of the books, taking your time. There is nothing here that needs to be solved. There is only something here to be witnessed. So let your eyes close, if they are not already closed. Let your body settle a little deeper into wherever you are resting. The universe outside this room is still expanding, still moving, still doing the slow, patient work it has been doing for 14 billion years. The galaxies are drifting outward. The stars are quietly burning. Somewhere far beyond your window, in the great dark fields between worlds, the future is gathering itself, slowly, gently, with all the time it needs. And in the next part of our journey, we will begin to walk toward that future, starting with the quietest ending of all, the one in which the universe simply, peacefully, runs out of fire. There is a law written into the fabric of everything. It is not a law that anyone made. It is not a law that can be changed or appealed or worked around. It is older than the stars and quieter than anything you have ever heard. Scientists call it the second law of thermodynamics, but what it describes is something you already know in your body, something you have felt 1,000 times without ever needing to name it. When you hold a warm cup of tea in your hands on a cold morning, the warmth moves outward. It spreads into your palms, into the air around the cup, into the table beneath it. It does not gather. It does not concentrate. It drifts, slowly and evenly, away from the cup and toward the rest of the world. And no matter how long you wait, no matter how still the room is, that warmth will never gather itself back. It will never flow from your cold hands back into the cup. It will never make the tea warm again on its own. The warmth moves in one direction only, outward, always outward. This is entropy. This is the great slow law that governs everything. Entropy is the measure of disorder in a system. When things are ordered, when energy is concentrated, when heat is gathered in one place and cold in another, entropy is low. When things are spread out, when energy is distributed evenly, when there is no difference in temperature from one place to another, entropy is high. And the law, the deep unbreakable law, says that entropy always increases. The universe always moves from order toward disorder, from concentrated to spread out, from warm and structured to cold and even. Always in that direction, never the other way. You can reverse entropy locally, in small ways, for short periods of time. A refrigerator concentrates cold. A living cell builds complex structures from simple ones. You, right now, are a temporary island of low entropy in a universe that is slowly drifting toward high entropy all around you. But every time you create local order, you create more disorder somewhere else. The refrigerator heats the room. The cell uses energy that came from somewhere and will end up as heat. Everything that fights entropy eventually adds to it. There are no exceptions. The universe itself is subject to this law. The entire cosmos, all the stars and galaxies and dark matter and radiation and everything else that exists, is a vast system sliding, slowly and irreversibly, toward a state of maximum entropy. A state in which all energy is perfectly spread out, all temperature differences gone, all gradients dissolved, all the quiet fires extinguished. That final state has a name. It is called heat death. Some call it the Big Freeze. It is the ending in which the universe does not explode or collapse or tear itself apart. It simply, patiently runs out of differences. And when there are no more differences, there is nothing left to drive any process, any motion, any change. The universe becomes a perfect, frozen, featureless stillness. This is the ending that most cosmologists today consider the most probable fate of the cosmos. Not the most dramatic ending, but perhaps the most honest one. The universe is already moving toward it. It has been moving toward it since the very beginning. Every star that burns, every wave that breaks, every heartbeat that moves blood through a body, is a small step in this direction. We are all, in our own ways, helping the universe drift toward its final rest. Let us walk through this ending slowly, step by step, the way you might walk through a museum after it has closed, the lights dimmed, the vast quiet spaces all your own. Right now, the universe is full of stars. There are somewhere between 100 billion trillion and 200 billion trillion stars in the observable universe. These are numbers so large, they do not quite land as numbers. They arrive in the mind and then drift away, too large to hold. So instead, think of it this way. If every grain of sand on every beach and desert on Earth represented one star, you would still not have enough grains of sand. The universe is that full of fire. It is, in this moment, in its long life, still blazing. Stars burn by a process called nuclear fusion. Deep in the core of every star, hydrogen atoms are being crushed together by gravity until they fuse into helium, releasing energy as they do. This energy is what makes stars shine. It is what warms your face when you stand in sunlight. It is what drives the wind and the rain and the growth of every plant that has ever grown on this earth. The sun has been doing this for about 4.5 billion years. It will do it for about another 5 billion. Then its hydrogen will begin to run out. When the hydrogen in a star's core is exhausted, the star does not simply go dark. It changes. For a star like our sun, the core will contract and heat up, while the outer layers expand, cooling and reddening, until the sun has swollen into what is called a red giant, so large it will swallow the inner planets. Eventually, the outer layers will drift away into space as a beautiful cloud of glowing gas called a planetary nebula. What remains at the center will be a small, dense object called a white dwarf. It is the core of the star, the spent ember, no longer fusing, but still holding heat. It will glow for a very long time, cooling slowly, like a coal taken from a fire and set on a stone. White dwarfs do not die quickly. They cool over trillions of years, slowly radiating their remaining heat into space. Scientists believe that the very last white dwarfs will still be faintly warm tens of trillions of years from now. The universe is currently 13.8 billion years old. Tens of trillions of years is roughly 1,000 times longer than the universe has currently existed. We are, in the story of stellar evolution, still very near the beginning. But the time will come, far further along than even that, when the last white dwarfs will have cooled completely. They will become what are called black dwarfs, cold, dark spheres of dense matter, drifting through a universe that has gone dark around them. They will not shine. They will not warm anything. They will be the bones of stars, the final remnants of all those billions of trillions of fires, and they will drift, silently, through the growing darkness. The galaxies themselves will have changed long before this. Right now, the universe is expanding, but within galaxies, gravity still holds things together. The Milky Way, your galaxy, the soft river of stars you can sometimes see on a clear, dark night, is held together by its own gravity. It is orbiting its own center, a slow, graceful wheel of several 100 billion stars. And in about 4 billion years, it will collide with our neighboring galaxy, the Andromeda Galaxy, in a slow merging that will last hundreds of millions of years and eventually produce a single larger galaxy. Galactic collisions are not violent in the way that word suggests. The stars are so far apart that almost none of them will physically collide. It is more like two swarms of fireflies drifting through each other. But over much longer timescales, even galaxies will begin to lose their shape. Stars at the edges of galaxies will gradually be flung outward through a process called gravitational evaporation, slowly escaping their home galaxy over timescales of 100 trillion years or more. The galaxies will grow thin and sparse, and all the while the expansion of the universe will be carrying them further and further apart from one another. There will come a time, far ahead of us, when the galaxies beyond our own local group will have receded so far that even light traveling at its full speed can no longer reach us from them. The expansion of space will be carrying them away faster than light can cross the distance. Those galaxies will simply vanish from our sky, slipping forever beyond a kind of cosmic horizon. The universe will not have shrunk. It will have expanded so much that each island of matter will be isolated in its own vast pocket of space, surrounded by an emptiness so complete that no signal, no light, no message can ever arrive from beyond it. This is one of the quieter features of the heat death scenario. The universe does not end all at once. It becomes lonely first. The sky empties out. The great community of galaxies that we can currently observe with our telescopes, those thousands and millions of distant lights, will one day be gone from view, not destroyed, only unreachable. Future astronomers, if they existed, would look out into a sky containing only their own galaxy, and they might be forgiven for thinking the universe was small and empty, when in fact it would still be vast beyond imagining. Now think about timescales for a moment, slowly, without rushing. The current age of the universe is 13.8 billion years. Write that number gently in your mind. Now consider that white dwarfs will still be cooling at 10 trillion years. That is roughly 700 times longer than the current age of the universe. Now consider that galaxies will have fully dissolved at around 100 trillion years. That is 7,000 times the current age. These are not numbers that fit inside human experience. They are numbers that can only be felt, the way you might feel the depth of an ocean by standing at its edge rather than diving to its bottom. And we have not even reached the most extraordinary part yet. Black holes, when the most massive stars burn out, they do not leave white dwarfs. They collapse. The core of the star implodes under its own gravity, crushing matter into a singularity of infinite density, and the result is a black hole. A region of space where gravity is so strong that nothing, not matter, not light, not any signal of any kind, can escape. Black holes are already ancient. The one at the center of the Milky Way, called Sagittarius A, contains the mass of 4 million suns compressed into a region smaller than our solar system. For a very long time, black holes were considered permanent. Once something fell in, it was gone. The black hole simply grew larger. But in the 1970s, Stephen Hawking made one of the most startling and beautiful discoveries in the history of theoretical physics. He showed, using a combination of quantum mechanics and general relativity, that black holes are not truly permanent. They radiate. Very slowly, almost unimaginably slowly, black holes leak energy into the surrounding space in the form of what is now called Hawking radiation. And as they radiate, they lose mass. Over time, slowly, a black hole evaporates. How slowly? A black hole with the mass of our sun would take about 2 times 10 to the power of 67 years to evaporate completely. That is a 2 followed by 67 zeros. The current age of the universe is written with 10 digits. The evaporation time of a solar mass black hole is written with 68. Now consider that the black holes at the centers of galaxies are millions or billions of times more massive than our sun, and their evaporation times are correspondingly longer. The supermassive black hole at the center of the Milky Way would take something in the range of 10 to the power of 87 years to evaporate, a 1 followed by 87 zeros. These are not years. These are almost not numbers. They are the quietest and most patient kind of time. But even these giants will eventually finish. One by one, across a span of time that makes all previous timescales seem brief, the black holes will radiate away their mass. They will grow smaller and smaller, warmer and warmer in their final moments, until they vanish in a last faint pulse of radiation. And when the last black hole is gone, the universe will enter a phase that has no precedent. No stars, no galaxies, no black holes, only the faintest background of radiation, growing thinner and thinner as the universe expands. Scattered particles of matter so far apart that they could spend the entire remaining age of the universe traveling toward each other and never arrive. A temperature so close to absolute zero that the difference from absolute zero itself would be almost meaningless. The universe, in this state, will have reached maximum entropy. There will be no more differences in temperature, no more concentrations of energy, no more gradients to drive any process whatsoever. Nothing will happen, not in a dramatic sense, not in a sudden sense, but in the deepest sense. No fire can start without a temperature difference. No information can travel without energy to carry it. No complexity can form because there is nothing to build it with. The universe will not be destroyed. It will be finished. It will be complete. Like a piece of music that has played its final note and let the last resonance fade into a perfect silence. Is this a sad thing? It does not have to be. There is a way of hearing this ending that is not about loss. Think about the state the universe would be in after heat death. Perfect equilibrium, perfect stillness. A kind of cosmic rest so complete that the word rest does not really do it justice. No turbulence, no uncertainty, no energy being borrowed and repaid. Everything settled, everything even. Everything, finally, quiet. The physicist Brian Greene has written about how the heat death is a state of maximum entropy, but it is also, in a way, a state of maximum symmetry. The universe would look the same everywhere. Every direction would be equivalent to every other direction. Every point in space would be indistinguishable from every other point. There would be a kind of perfection in it, the perfection of pure sameness, pure rest, the way a perfectly still lake is perfect in its stillness, even though nothing is happening in it. The Buddhist traditions have a concept called nirvana, which is sometimes translated as the extinguishing of a flame. The heat death of the universe is not the same thing, and we should be careful not to force too much meaning onto a scientific concept. But there is something in the image that resonates. The universe, after an unimaginably long process of burning and transforming and changing, finally extinguishes. Not in defeat, in completion, and here is the thought to carry for a moment before we continue. The heat death is not a thing that happens to the universe. It is a thing the universe does. It is the natural conclusion of all the processes that have been running since the beginning. Every star that burns, every galaxy that forms, every planet that holds water and life and breath, every one of these things is a temporary eddy in the flow toward equilibrium. They are the universe being beautiful and complex, on its way to being simple and still. We are one of those eddies. Not a mistake, not a detour, a natural and extraordinary part of the journey. The reason most cosmologists consider heat death the most likely fate is that it follows from two things that seem to be true. The first is the second law of thermodynamics, which has never once been observed to be violated in any system anywhere. The second is the current observational evidence that the universe is expanding and will likely continue to expand forever, driven by dark energy, never reversing, never contracting, giving entropy the time and space it needs to finish its work. These are not certainties. Science does not traffic in certainties, but they are the strongest guides we currently have. The data from the best telescopes, the most sensitive instruments, the most careful measurements of the expansion rate of the universe, all of it points toward an open, ever-expanding cosmos that will eventually cool into silence. The heat death is not a guess. It is the extrapolation of the deepest physical laws we know, carried forward across unimaginable time. It is fitting that this ending, the most likely ending, is also one of the most peaceful. Not a catastrophe, not a ripping apart, not a collapse, just the slow, patient, inevitable cooling of all the fires in the universe, one by one, across a span of time so vast that you would need to spend your entire life just reading out the number of years involved. The universe began in unimaginable heat. It will end in unimaginable cold. And in between, for a brief and blazing middle period, it held things like stars and planets and water and life and you, lying quietly in the dark, listening to the sound of your own breathing. Let that settle for a moment. Let the image of the last light slowly cooling into nothing be not a frightening image, but a restful one. The universe is not in a hurry. It never has been. It will take all the time it needs. In the next part of our journey, we will leave the gentle darkness of heat death and visit a stranger and more turbulent ending, one where the universe does not cool slowly, but is torn apart, piece by piece, by a force we still do not fully understand. It is called the Big Rip, and it begins, as all the most interesting things begin, with a mystery. There is something in the night sky that does not show up in any photograph. It does not glow. It does not cast shadows. It does not interact with light in any way that our instruments can directly detect. And yet, it makes up roughly 68% of everything that exists in the universe. It is the dominant component of the cosmos, the single largest ingredient in the recipe of reality, and we do not know what it is. We have given it a name, the way you might give a name to a sound you hear in the walls of an old house, not because the name explains it, but because naming it makes it easier to talk about. We call it dark energy. And if it behaves in a certain way, it will not just shape the ending of the universe, it will shred it. Let us begin where the discovery began, because the story of how dark energy was found is one of the most quietly astonishing stories in the history of science. It begins in the 1990s, with two teams of astronomers who were trying to do something very precise and very careful. They were trying to measure how fast the expansion of the universe was slowing down. Notice the assumption built into that sentence. They were not trying to determine whether the expansion was slowing. They assumed it was. Every physicist, every cosmologist, every researcher working on the question at the time believed that the expansion must be decelerating. The reason was simple and sensible. The universe is full of matter, and matter has gravity, and gravity pulls things together. So while the initial explosion of the Big Bang had sent everything flying outward, gravity should have been working against that expansion ever since, tugging at galaxies, slowing the whole outward rush, the way the Earth's gravity slows a ball thrown upward into the air. The question was not whether the expansion was slowing. The question was how fast. To measure this, both teams used a particular kind of exploding star called a Type 1, a supernova. These explosions are remarkable tools for cosmologists, because they are, to a very good approximation, all the same brightness. When a white dwarf star reaches a certain critical mass and explodes, it releases a very consistent amount of energy. This means that if you see one of these supernovae in a distant galaxy, you can calculate how far away it is by how bright it appears. The dimmer it looks, the further away it is. They are cosmic measuring sticks spread across the universe, each one a reliable marker of distance. Both teams gathered data on dozens of these supernovae in distant galaxies. They were comparing how fast the galaxies were moving away from us to how far away they were, looking for the signature of deceleration, the slight evidence that the expansion was being pulled back by gravity. And in 1998, both teams independently arrived at the same result, a result that stopped them cold. The expansion was not slowing down, it was speeding up. The distant supernovae were dimmer than they should have been if the expansion were decelerating. They were further away than expected. The universe was not just expanding, it was expanding faster and faster. Something was pushing outward, not pulling inward, and that something was winning against gravity on the largest scales. The universe was accelerating. The teams checked their data again. They looked for errors. They considered every alternative explanation they could find, but the result held. In 2011, the scientists who led this discovery, Saul Perlmutter, Brian Schmidt, and Adam Rees, received the Nobel Prize in Physics for it. The universe, the cosmos, that was supposed to be decelerating under its own gravity, turned out to be accelerating instead. Something was pushing it outward. Something that fills all of space, exerts a kind of pressure that works against gravity and grows stronger as space expands. That something was dark energy, and its discovery quietly rewrote our understanding of the fate of the universe. Now here is the crucial thing about dark energy that determines which ending the universe will meet. We do not know if dark energy is constant or changing. This is not a small uncertainty. It is one of the deepest open questions in all of physics. If dark energy stays constant, if it maintains the same strength forever as the universe expands, then the most likely ending is the heat death we visited in the last part. The universe expands forever. Things slowly cool and fade, and eventually all the lights go out in a gentle, patient way. But if dark energy grows stronger over time, if it becomes more powerful as the universe ages, then the ending is something altogether different. Then the ending is what physicists call the Big Rip. The Big Rip is not a gradual fading. It is an unbinding. It is the universe coming apart at every level of its structure, from the largest scales down to the smallest, piece by piece, in a cascade that is both slow and absolute. It begins so gently you would not notice it for billions of years, and it ends in a moment of total dissolution, a final instant in which the fabric of space itself tears. Let us walk through it. The key to the Big Rip is a quantity called the phantom energy equation of state, but you do not need to hold that phrase. What you need to hold is the idea. If dark energy is a kind of phantom energy, a form of energy whose pressure grows more negative over time, then its repulsive effect on space grows stronger and stronger as the universe expands. And as it grows stronger, it begins to overwhelm not just the gravity holding galaxy clusters together, not just the gravity holding individual galaxies together, but eventually every force of attraction at every scale in the universe. It overcomes gravity first, then the electromagnetic force, then ultimately the strong nuclear force, the force that holds the nuclei of atoms together. One by one, the forces that hold things together are outrun by the growing push of phantom energy, and one by one, the structures those forces maintain come apart. The first things to go are the largest structures in the universe, the great filaments and walls and clusters of galaxies that make up what astronomers call the cosmic web. Right now, the universe has structure. Matter is not spread out evenly. It clumps into galaxies, and those galaxies gather into clusters, and those clusters link together in vast filaments, like the threads of a spider's web stretching across the observable universe. This structure has been built up over billions of years of gravitational attraction. It is one of the most beautiful things about the cosmos, this intricate web of matter hanging in the dark. In the Big Rip scenario, this web begins to dissolve first. The growing force of dark energy starts to pull at the bonds between clusters of galaxies. The filaments begin to thin and break. Galaxy clusters separate from one another, the distances between them growing faster than anything can travel to maintain connection. This happens over a vast timescale, billions of years before the final rip, and it is gradual enough that nothing dramatic is visible within any individual galaxy. The universe simply becomes lonelier. The clusters drift apart. The web unravels. Think about what this means in scale. The Virgo cluster, the nearest large cluster to our own local group of galaxies, contains more than 1,000 individual galaxies. It is roughly 60 million light-years from here. In the beginning of the Big Rip scenario, that distance simply grows and grows until the cluster is unreachable, then invisible, then gone beyond any possible horizon. The community of galaxies that has spent billions of years forming and gravitating together simply drifts away, like leaves on a slow river that has grown too wide to cross. Then, closer in, the same thing begins to happen to individual galaxies. A galaxy is held together by the combined gravity of all its stars, its gas, its dark matter. The Milky Way, your galaxy, is a gravitationally bound system. Its stars orbit the galactic center at hundreds of kilometers per second, and that orbit is a balance between the outward tendency of motion and the inward pull of gravity. In the Big Rip, as dark energy strengthens, it begins to interfere with this balance. The pull of gravity within the galaxy is slowly, gradually, insufficiently overcome by the growing repulsive pressure of phantom energy. Stars at the edges of the galaxy are the first to drift away. Then the galaxy begins to thin, to spread, to lose its spiral structure, to dissolve from a graceful wheel of stars into a scattered cloud of lonely suns. Eventually, the galaxy itself is gone. Not destroyed, dispersed. Its stars are still there, each one still burning, but they are no longer connected to each other by any gravitational thread. Each star is its own small island in an expanding void. Now come closer still. Now think about solar systems. In a solar system like ours, the planets orbit the Sun in paths maintained by the balance of gravity and velocity. The Earth has been orbiting the Sun for 4.5 billion years without any difficulty because gravity is strong enough at this scale to hold the orbit stable. But in the final stages of the Big Rip, as dark energy grows into a dominant force at smaller and smaller scales, even this balance begins to fail. The orbits of the outer planets are disrupted first. Neptune, Uranus, the distant cold worlds at the edge of the solar system find their orbits destabilized. They spiral outward, slowly uncoupled from the gravitational pull that has kept them in place for billions of years. Then the inner planets follow, then the Earth itself. Imagine the Earth's orbit around the Sun slowly widening, not quickly, not with any immediate drama. Just the gentle, patient, unstoppable widening of a spiral, the planet drifting further from its star as the force that binds them is outrun. The Earth would cool as the distance grows. The oceans would eventually freeze. But all of this is a very minor detail in the context of the Big Rip, because shortly after solar systems come apart, something even more fundamental begins to dissolve. Planets themselves. A planet is held together by its own gravity. The Earth is a sphere because gravity pulls all its material inward toward the center. The rock and iron and water of the Earth are all in a kind of equilibrium, held together by the planet's own mass pulling inward. As dark energy grows still stronger, even this self-gravity begins to fail. The material of planets begins to be pulled apart, not all at once, not in an explosion, but in a slow structural failure, the way a building might begin to separate at its joints before it falls. The outer layers of the planet are pulled away first, then deeper and deeper into the interior, until what was once a world is a dispersing cloud of rock and metal and gas, spreading slowly into the void. By this point in the Big Rip timeline, we would be in the final hours, not the final billion years, not the final million years, the final hours. This is one of the most striking things about the cascade of the Big Rip. Most of it happens slowly, over cosmological timescales that are nearly impossible to imagine. But the final stages of the dissolution, the tearing apart of matter itself, happen with increasing speed. Because the phantom energy grows in proportion to the expansion of space, and the expansion of space accelerates as the phantom energy grows, the whole process feeds on itself. The closer you get to the end, the faster things come apart. In those final hours, the dissolution reaches the level of individual objects. Rocks are pulled apart. Dust is scattered. Water molecules are stretched until the bonds between their atoms break. The chemistry of the universe, the intricate molecular architecture that makes everything from minerals to the proteins in your body, all of it comes undone. Not because of heat, not because of radiation, but simply because the space between atoms is being expanded faster than the electromagnetic forces that bind atoms together can maintain. Molecules separate into individual atoms, drifting apart into a space that is growing too fast for them to stay close. And then the atoms themselves. An atom is a nucleus surrounded by electrons, held together by electromagnetic force. The electrons are bound to the nucleus because the attractive force between their opposite charges is strong enough to keep them in orbit. But in the final moments of the Big Rip, even this is not strong enough. The electrons are pulled away from the nuclei. Atoms are stripped bare. The universe becomes a plasma of free electrons and free nuclei, each one isolated in an expanding void, none of them connected to anything else. And then the nucleus of an atom is held together by the strong nuclear force, the most powerful of the four fundamental forces of nature. It is the force that binds protons and neutrons together at distances so small they make atoms look enormous. Nothing in ordinary physics can overcome the strong nuclear force. It is what makes matter solid at its most fundamental level. But the phantom energy of the Big Rip does not care about the strong nuclear force. In the very final fraction of the very final second, the growing expansion of space reaches down to the scale of atomic nuclei and pulls even these apart. Protons and neutrons separate, and if the energy grows strong enough, even those particles may be torn into their constituent quarks. And then there is nothing to tear. The rip is complete. What the Big Rip leaves behind is not darkness in the way heat death leaves darkness. Heat death leaves a cold, sparse universe full of particles that are simply too spread out to interact. The Big Rip leaves something more thorough. It leaves a universe in which even the smallest pieces of matter have been separated from one another, a universe in which the very fabric of space has been expanded to a state of infinite dilution in a finite amount of time. The end point of the Big Rip is a kind of absolute dissolution, a universe returned to its most scattered and disconnected state. But let us not rush past the strangeness of the timing. According to the models developed by physicists Robert Caldwell, Mark Kamionkowski, and Nevin Weinberg, who first published a detailed analysis of the Big Rip in 2003, the approximate sequence of events in the final era would unfold over a very particular timeline. Galaxy clusters would be disrupted roughly 29 million years before the final rip. Individual galaxies would come apart about 60 million years before. Solar systems would be unbound about 3 months before. Planets would be torn apart approximately 30 minutes before. And atoms would dissolve in the final fraction of a second. Sit with that for a moment. The entire final era, from the dissolution of galaxy clusters to the dissolution of atoms, spans roughly 60 million years. And yet the last 30 minutes of those 60 million years account for the destruction of every planet in the universe. The last fraction of a second accounts for the dissolution of every atom. The end accelerates toward itself. The closer it gets, the faster it arrives. There is something almost musical about this structure, a long, slow prelude of billions of years, then a gradual quickening, then a sudden finale that compresses the destruction of all matter into a moment too brief to perceive. The Big Rip is not an ending that arrives uniformly. It arrives the way a wave arrives at a shore, slow and rising, and then, all at once, crashing. Now, step back from the cascade and think about what it means. The Big Rip is a deeply strange ending because it is, in a sense, the most thorough. Heat death leaves matter intact, just too spread out to interact. The Big Crunch, which we will visit in the next part, compresses matter back to a point, but the Big Rip dissolves matter at every scale. It does not just separate things from each other, it returns everything to its smallest possible pieces. Every proton, every electron, every quark, every field, stripped of every bond, every connection, every relationship. The universe at the end of the Big Rip is not dark, it is not compressed. It is returned to a state of absolute simplicity, absolute disconnection. Everything that was ever built, every star, every planet, every molecule of water, every moment of chemistry, dissolved back into its basic ingredients. There is a way of holding this that is not violent. The word rip carries a sharpness that the actual process would not have, at least not until its very end. For the vast majority of its duration, the Big Rip would be as slow and patient as anything in cosmology. The galaxies would drift apart over millions and billions of years. The stars would continue to burn for most of that time. The universe would still be full of fire and complexity right up until the last few 100 million years. And even then, the dissolution would be gradual by human standards, far too gradual to witness directly. Only at the very end, in the final hours and minutes and fractions of seconds, would the process become sudden. And by then, there would be nothing left with eyes to see it or a mind to understand it. The Big Rip is not a story about violence. It is a story about the ultimate unraveling of a universe that has been building complexity for billions of years. It is, in its own strange way, a kind of reversal of the arrow of time. Creation built atoms from quarks, molecules from atoms, planets from molecules, life from chemistry, stars from gas. The Big Rip reverses all of that, one level at a time, until only the quarks remain, and then even they are free. Whether this ending will actually arrive depends entirely on one of the most important unanswered questions in all of physics. What is dark energy, and is it changing? If dark energy is the cosmological constant that Einstein once imagined, a fixed and unchanging energy density built into the fabric of space itself, then it will not grow stronger over time, it will stay the same. The universe will continue to expand, but the expansion will not accelerate into a rip. Heat death remains the likely outcome. But if dark energy is something else, something dynamic, some field that evolves over time, then it could grow. And if it grows in the particular way that phantom energy grows, the Big Rip follows as surely as dawn follows night. Right now, our best measurements of dark energy suggest that it is very close to being constant. The data from the Planck satellite, which mapped the cosmic microwave background with extraordinary precision, and the data from large surveys of galaxy positions and supernovae, all suggest that dark energy looks within our current ability to measure it, like a cosmological constant. It does not appear to be growing, but the uncertainties in these measurements are still significant enough that we cannot rule out the possibility that dark energy is slowly changing. The difference between a constant dark energy and a slowly growing dark energy is small enough that our current instruments cannot definitively tell them apart. This is what makes the question so extraordinary. The difference between the heat death and the Big Rip, between a universe that cools slowly over a near infinite timescale and a universe that is torn apart in a finite time, may depend on a difference in dark energy's behavior so small that we cannot yet measure it. The fate of everything hangs on a distinction that is currently beyond our precision, and that is not a frustrating thought. It is a wonderful one. It means the universe still holds its ending as a secret, a mystery encoded in the behavior of a force we have only known about for a little over 2 decades. What is dark energy really? Where does it come from? Is it a property of space itself, or is it a field that fills space? Is it a remnant of some earlier event in cosmic history, or is it a fundamental feature of reality? Is it truly constant, or is it slowly evolving? These questions are at the frontier of everything we are trying to learn about the universe. Major space missions, including the European Space Agency's Euclid telescope, currently observing the sky, are designed specifically to measure the behavior of dark energy with greater precision than ever before. The data they return over the coming years may help us understand whether dark energy is changing, and if so, in which direction. Until that answer arrives, the Big Rip remains what it has always been, a genuine possibility, a real and scientifically grounded scenario for the ending of everything. Not the most likely ending by current reckoning, but not a fantasy either. It is a possibility that follows directly from the physics we know, extended forward in time under a specific set of conditions that we cannot yet rule out. It is the universe's way of saying that even its most fundamental properties are still unfolding their meaning to us. We are still learning the story. We are still in the early chapters. There is something softening about this. We live in a universe whose fate we do not fully know. We live in a cosmos that has not yet revealed whether it will fade quietly, or unravel dramatically, or collapse, or bounce, or do something we have not yet imagined. And this uncertainty is not a problem. It is the condition of being alive in a universe that is still in the middle of its own story. The mystery is not something to resolve before you can rest. It is something to carry gently, the way you carry a question you love, one that you are in no hurry to answer, because the asking of it is itself a kind of gift. Let your breath slow down now. Let the image of the universe slowly unbinding, of galaxies drifting apart and atoms floating free, be not a frightening image but a spacious one. There is so much room in the Big Rip, so much emptiness, so much quiet between the pieces. Even in its most dramatic ending, the universe offers space and silence in abundance. In the next part of our journey, we will leave the unbinding and visit its opposite. We will visit the theory in which the universe does not spread out forever, but instead reverses, draws inward, collapses back toward its own center. We will visit the Big Crunch and the beautiful possibility that follows from it. The possibility that an ending might be nothing more than the universe drawing a deep breath before it begins again. There is a different way to think about endings. Not as a final state, not as a last moment after which nothing follows, but as a turning point, a place where one thing becomes another, where the last note of a piece of music is also in some sense the silence that makes the next piece possible, where the final breath out is the condition for the next breath in. There are theories about the fate of the universe that hold this kind of shape. They are theories not of ending but of return, and they begin with a question that is older than any telescope, older than any equation. What if the universe comes back? Before dark energy was discovered, before the accelerating expansion changed everything cosmologists thought they understood about the future of the cosmos, the most natural ending most physicists imagined for the universe was not a gradual fading and not a tearing apart. It was a return. It was the universe reversing itself, drawing all its scattered matter back together, collapsing inward the way it once expanded outward, until everything that exists is once again compressed into a single, unimaginably hot and dense point. This ending has a name that carries its own quiet drama. It is called the Big Crunch. The logic behind the Big Crunch is simple and beautiful and feels almost inevitable once you understand it. The universe began with an explosion, or something like an explosion, a moment of extraordinary density and heat from which everything expanded outward. As it expanded, matter was spread through space, and that matter has gravity. And gravity is a force of attraction, a force that pulls things together. So even as the universe expanded, gravity was working against that expansion, tugging at the edges, pulling at the galaxies, trying to slow the outward rush. The question, for most of the 20th century, was whether gravity would win. Think of it this way. If you throw a ball straight up into the air, one of two things will happen. If the ball is moving fast enough, it will escape the Earth's gravitational pull and travel outward forever. If it is not moving fast enough, gravity will slow it, stop it, and pull it back down. The outcome depends on the balance between the initial speed and the strength of the gravitational pull. The same logic applies to the universe. If the expansion is fast enough, or if the density of matter is low enough, the universe expands forever. If the expansion is slow enough, or if the density of matter is high enough, gravity eventually wins. The expansion slows, stops, and reverses, and everything falls back. For most of the 20th century, cosmologists did not know which of these two futures awaited the cosmos. They measured the density of matter in the universe and compared it to a critical value, a threshold that would determine the fate of everything. If the density was above the critical value, the universe would collapse. If it was below, it would expand forever. If it was exactly at the critical value, the universe would expand forever, but more and more slowly, approaching stillness without ever quite reaching it. The measurements were difficult, and for a long time the answer was genuinely uncertain. The Big Crunch scenario, the collapsing universe, felt to many physicists like a satisfying ending. Not a comfortable one, perhaps, but a complete one. There is a kind of symmetry in it, a narrative symmetry, that the human mind finds naturally appealing. The universe began in a moment of extreme compression. It expanded, it aged. It formed stars and galaxies and planets and life. And then, slowly, gravity reasserted itself. The expansion slowed. It stopped. The distant galaxies, which had been rushing away from each other for billions of years, began to approach each other instead. The light from other galaxies, which had been stretched toward the red end of the spectrum by expansion, would now be compressed toward the blue end by contraction. The sky would slowly brighten as galaxies drew together. The temperature of the cosmic background radiation, the faint warmth left over from the Big Bang, would gradually rise as space contracted and that radiation was compressed back into a smaller volume. The process would take billions of years to become dramatic, and then it would accelerate. Galaxies would merge, galactic clusters would press together, the distances between stars would shrink. The sky would fill with light as more and more galaxies piled into the same region of space, and the temperature would rise and rise and rise until the heat was enough to strip the electrons from atoms, until the atoms themselves were broken apart, until the subatomic particles that make up all matter were compressed into a density that has no analogy in ordinary experience. And finally, in a moment that mirrors but reverses the Big Bang, everything would be crushed back into a single point of infinite density and temperature, the Big Crunch. What happens at the Big Crunch itself is a place where our current physics breaks down. Just as the very first moment of the Big Bang is a singularity, a point where the equations cease to be meaningful, the Big Crunch is also a singularity. We cannot see through it using the tools we currently have. It is a wall in our understanding, and for a long time, most physicists assumed it was simply the end, the singularity, the point, the nothing. The universe folded back on itself and ceased to exist. But some physicists looked at that singularity and wondered if it was not an ending at all. What if the singularity is not a termination but a transition? What if the extreme conditions at the moment of maximum compression do not destroy the universe but instead trigger a new expansion? What if the Big Crunch and the Big Bang are the same kind of event, viewed from different sides of the same moment? What if the universe, rather than ending, bounces? This is the Big Bounce. It is an idea that has appeared in different forms across the history of cosmology, but it carries a consistent and profound image at its heart. The universe does not end. It compresses to a maximum density, a moment of extraordinary energy and heat, and then The compression itself generates the conditions for a new expansion. The cosmos bounces back outward. A new universe begins. And perhaps this has happened before, many times, across a span of time without beginning or end. Perhaps our universe is one in a long, long series of universes, each one expanding from the echo of the one before it, each one eventually collapsing or reaching its own end and giving rise to the next. The cosmos breathing in and out, forever. There is something deeply comforting in this image, if you let yourself sit with it. The universe is not a single event with a beginning and an end. It is a rhythm, it is a pulse. Every ending contains within it the seed of the next beginning, the way every winter contains, buried in its frozen ground, the seeds of the next spring. Nothing is truly lost, nothing is truly finished. The universe is not a story that ends, it is a story that breathes. The Big Bounce has been explored in several distinct theoretical frameworks over the years. One of the most developed is called loop quantum cosmology, a branch of theoretical physics that attempts to apply quantum mechanics to the structure of space and time itself. In ordinary general relativity, the equations that describe how space curves and bends under gravity break down at a singularity. The density becomes infinite, the temperature becomes infinite, the equations produce meaningless results. But in loop quantum cosmology, the structure of space itself is quantized, meaning it comes in tiny discrete units rather than being perfectly continuous. And when you apply this quantized structure to the conditions near a singularity, something remarkable happens. The singularity does not form. Instead of density becoming infinite as the universe contracts, a quantum repulsive force becomes dominant at extremely small scales and halts the collapse. The contraction stops, and the universe expands again. In this framework, what we experience as the Big Bang, the beginning of our universe, would actually be the bounce, the moment when a previously contracting universe reached its minimum size and reversed. Our universe would not have come from nothing. It would have come from the end of a previous universe, one that contracted until its quantum structure pushed back and launched the expansion we now live in. And when our universe eventually reaches its own end, whether through heat death or some other fate, another cycle might begin. Sit with that thought gently. You are living inside a breath. The universe breathed in from the last cycle, and one day it may breathe out again into the next. The atoms in your body have been through this before, in some form, in the previous universe, and they will go through it again in the next one. Nothing is lost. Everything is transformed. But the Big Bounce, beautiful as it is not the only theory that imagines a cyclic cosmos. There is another framework, one that is more mathematically precise and in some ways more philosophically astonishing, developed by one of the great mathematical physicists of our time. His name is Roger Penrose, and his theory is called conformal cyclic cosmology. Roger Penrose is not a physicist who deals in vague ideas. He is one of the most rigorous mathematical thinkers alive, the man who, alongside Stephen Hawking, proved theorems about the inevitability of singularities in general relativity. When Penrose proposes something, it comes with mathematics attached. And what he has proposed in conformal cyclic cosmology is a vision of the universe so strange and so elegant that it deserves to be visited very slowly. The starting point of Penrose's theory is a deep mathematical observation about the two extreme states of the universe. The first extreme state is the very beginning, the Big Bang, a moment of extraordinarily low entropy, very high density, and very high temperature. The second extreme state is the very end, the heat death, a universe that has expanded for an unimaginable time until it contains almost nothing but a faint and growing fainter background of radiation. All the black holes evaporated, all the matter dispersed, all structure dissolved. A cold, dark, enormously spread out cosmos. These two states seem like complete opposites. One is hot, dense, small, and energetic. The other is cold, sparse, vast, and almost empty. How could they possibly be related? Penrose's insight draws on a property of physics called conformal geometry. Conformal geometry is the study of shapes and angles, as opposed to distances and sizes. In a conformal transformation, you can rescale everything, make the whole universe larger or smaller, as long as you preserve the local angles between things. And Penrose noticed something astonishing. In the very far future of the universe, in the heat-death state, when all massive particles have either decayed or been dissolved and only massless radiation remains, something strange happens to the mathematics of space and time. Without massive particles, there is no way to measure the passage of time. Without a sense of scale, there is no way to measure size. The universe becomes, in a mathematically precise sense, conformally equivalent to the kind of state that could have been the beginning of a new universe. In other words, the cold, dark endpoint of one universe is, mathematically speaking, indistinguishable from the hot, dense beginning of the next. The ending and the beginning are the same thing, seen from different sides of a conformal rescaling. The death of one universe is not followed by the birth of another. It is the birth of another. The two events are, in the language of conformal geometry, the same event. Penrose calls each cycle an aeon. Our universe is one aeon, in a potentially infinite sequence of aeons, each one emerging from the conformally rescaled remnant of the one before. There was an aeon before ours. There will be an aeon after ours. And each aeon is, in some sense, complete in itself, a whole universe, with its own stars and its own planets and its own long, slow history, while also being part of an infinite chain of aeons stretching backward and forward without beginning or end. This is a thought that sits at the edge of what the human mind can hold. An infinite series of universes, each one emerging from the death of the last, each one full of fire and complexity and the possibility of awareness, each one eventually fading, its remnant becoming the seed of the next. The cosmos is not a story. The cosmos is a library, and every universe is one book in a collection that has no first shelf and no last. There is even, in Penrose's theory, the possibility of a kind of memory between aeons. The final events of the previous aeon, particularly the evaporation of supermassive black holes in the distant future, might leave faint imprints in the structure of the new aeon's cosmic microwave background. These imprints would appear as subtle circular patterns in the map of the cosmic microwave background radiation, the faint glow of heat left over from our own Big Bang. Penrose and his colleague Vahe Gurzadian have searched for these patterns and have reported finding what they believe may be evidence of them. This claim is controversial, and most cosmologists regard it with caution. The patterns are subtle, and there are plausible alternative explanations. But the possibility is extraordinary. The idea that our universe might carry, encoded in its most ancient light, the ghost of a previous universe, is one of the most haunting and beautiful ideas in modern physics. There is another version of the cyclic cosmos that deserves a gentle mention. It comes from string theory and a branch of cosmology called the ekpyrotic model. In this theory, our universe is a three-dimensional membrane, a brain, floating in a higher dimensional space. There is another brain nearby, and every trillion years or so, the two brains collide. The collision releases an enormous amount of energy, and this energy is what we experience as the Big Bang. After the collision, the brains drift apart, the universe expands and cools, and forms stars and galaxies, and eventually fades. And then, after another vast span of time, the brains drift close again and collide once more, triggering a new Big Bang, a new cycle. In this model, the universe is renewed not by bouncing from a singularity, but by collision with another universe, a neighbor we can never see or touch, but whose periodic approach has been generating new universes for an eternity. Each of these cyclic models carries a different set of mathematics and a different set of physical assumptions. They are not all the same theory, but they share a common spirit, a common intuition that the universe is not a one-time event. They share the sense that what we call the beginning was not a beginning in any absolute sense, and what we might call the ending will not be an ending in any absolute sense. They suggest that the cosmos is a process, a self-renewing process, one that has been going on before we arrived and will continue after we are gone. It is worth pausing to ask why these ideas are beautiful, not just in the poetic sense, but in the scientific sense. Beauty in physics is not merely aesthetic, it is often a guide. The great physicist Paul Dirac once said that it is more important for a physical theory to have beauty than for it to agree with experiment. That is a strong claim, and not everyone would go that far. But there is something to it. The most successful physical theories have tended to be the ones with a certain mathematical elegance, a quality of inevitability, of fitting together so naturally that they feel like they were already there waiting to be found. The cyclic models have this quality. There is an elegance in the idea that an ending and a beginning are the same event seen from different perspectives. There is a rightness in the image of a universe that does not waste itself, that turns its endings into beginnings, that keeps everything in play. But beauty is not evidence, and here we must be gentle and honest. The current observational evidence does not favor the cyclic models. The discovery of dark energy and the accelerating expansion of the universe poses a serious challenge to the Big Crunch scenario, which requires the expansion to reverse. With dark energy driving the expansion to accelerate, the conditions for a classical Big Crunch seem increasingly unlikely. Loop quantum cosmology and the Big Bounce remain active areas of theoretical research, but they have not yet produced clear and unique observational predictions that have been confirmed. Penrose's conformal cyclic cosmology remains highly controversial, with the claimed evidence for circular patterns in the cosmic microwave background disputed by many researchers. None of this means these theories are wrong. Science does not work by ruling theories out on the grounds that current evidence does not support them. It works by testing, refining, gathering more data, and seeing which theories survive contact with new observations. The cyclic models are alive. They are being worked on by serious physicists. New data from telescopes and observatories may one day shed clearer light on whether any of them are correct. And the history of science is full of cases where a theory that seemed unlikely, given the evidence available at a particular time, turned out to be the right one. The Big Bounce, the conformal cyclic cosmology, the ekpyrotic model, these are not wishful thinking. They are not mythology dressed in equations. They are genuine scientific proposals built on real mathematics, making real claims about the structure of reality. They are harder to test than the heat death scenario, and their predictions are more difficult to distinguish from those of competing theories. But they exist. They are coherent, and they offer something that no amount of skepticism can take away. The possibility that the universe does not end, that it is instead a cycle without ending, a breath drawn and released across a span of time that has no beginning and no edge. There is something in this possibility that the mind touches only lightly and then lets go, the way you might hold a very beautiful and fragile thing for a moment before setting it back down. The idea that there was a universe before ours, that there will be a universe after ours, that the Big Bang we trace our existence back to was itself the echo of something that came before, a previous cosmos whose long life ended in a way that seeded our own beginning. We cannot see that previous universe. We cannot measure it directly. We may never be able to, but the mathematics allows it. And in the space that mathematics opens, the imagination can walk quietly. You were born in a universe that may itself have been born from another universe. The atoms you are made of may have spent a previous aeon inside different stars, different planets, different forms. The light that currently fills the cosmic background of our sky may carry, somewhere in its subtle patterns, the faintest memory of things that happened before our universe was new. This is not a poetic conceit. It is a possibility taken seriously by people who spend their lives doing the most careful mathematics our species has produced. Let that settle gently. Let the image of a breathing cosmos be with you for a moment before we continue. In and out, expanding and contracting, dying and being reborn. Not once, but endlessly. Not here and then gone, but here and then here again, in a different form, with different stars and different arrangements of matter, but with the same fundamental laws, the same basic physics, the same deep tendency of matter to arrange itself into complexity and light. In the next part of our journey, we will leave the large-scale structures of the universe and descend into something stranger. We will visit the quantum world, where the laws of physics themselves might be uncertain, where empty space turns out not to be empty at all, and where the ending of the universe might come not from any large-scale force, but from a tiny bubble forming in the heart of the vacuum. We are going to visit some of the most exotic and least understood possibilities for the fate of everything. They are quiet possibilities, strange ones, and in their strangeness, they are perhaps the most beautiful of all. There is a question that lives at the very edge of what physics can currently ask. It is not a question about stars or galaxies or the large-scale structure of the cosmos. It is a question about empty space, about nothing, about whether the nothing that fills the universe between its visible contents is as stable and permanent as it appears, or whether it is, in a sense that takes a moment to understand, sitting on a ledge. This is where our journey tonight becomes its strangest and its most quietly astonishing. We have visited the slow cooling of heat death, the unbinding cascade of the Big Rip, the collapsing return of the Big Crunch, and the breathing rhythm of the cyclic cosmos. Each of those endings operates at large scales, the scales of galaxies and expansion rates and gravitational forces spread across billions of light years. But the possibilities we are going to visit now are different. They come from the smallest scales imaginable. They come from the quantum world, the level of reality where matter and energy behave in ways that have no analogy in ordinary experience, where particles appear from nothing and vanish back into nothing, where the very concept of empty space turns out to be misleading. In the quantum world, the fate of the universe is written in a language so small and so strange that we are only beginning to learn its alphabet. Let us begin with the vacuum. When physicists use the word vacuum, they do not mean simply an absence of matter. They mean something more precise and more surprising. The quantum vacuum is the lowest energy state of a region of space. The condition space is in when it contains no particles, no radiation, nothing that can be directly detected. And yet the quantum vacuum is not truly empty. It is alive with fluctuations. Virtual particles constantly appear in pairs, a particle and its antiparticle, existing for a tiny fraction of a second before annihilating each other and vanishing. These fluctuations are not hypothetical. They produce measurable effects. They contribute to the energy of atoms. They generate a small but detectable force between closely spaced metal plates, a phenomenon called the Casimir effect. The vacuum hums, very quietly, with a kind of borrowed energy that is always flickering in and out of existence. But here is the question that makes physicists pause. How do we know that the vacuum state we observe, the quantum vacuum of our universe with its particular set of physical laws and constants, is the true lowest energy state? How do we know that there is not a deeper vacuum, a more stable configuration of the quantum fields that fill all of space, one with lower energy than the state we currently inhabit. In the mathematics of quantum field theory, the fields that permeate all of space can exist in different energy states, the way a ball can rest in different dips and hollows on a rolling landscape. A ball resting in a shallow dip might appear stable. It will stay there as long as nothing disturbs it too much. But if there is a deeper valley nearby, separated by a hill, the ball can potentially tunnel through that hill, a quantum mechanical process with no classical analogy, and settle into the deeper, more stable valley. The shallow dip is called a false vacuum. The deeper valley is called the true vacuum, and the process of tunneling from one to the other is called vacuum decay. If our universe is currently in a false vacuum state, sitting in a shallow dip in the energy landscape of space rather than the deepest possible dip, then there is a probability, very small but not zero, that somewhere in the universe, a tiny region of space will quantum tunnel into the true vacuum. This region would be a bubble, a sphere of true vacuum, embedded in the false vacuum of our universe. And because the true vacuum has lower energy, it is more stable. The bubble would not remain small. It would expand. The wall of the bubble, the boundary between the true vacuum inside and the false vacuum of our current universe outside, would expand outward at the speed of light. And as it expanded, it would rewrite everything it passed through. The laws of physics as we know them, the particular values of the constants of nature, the specific strengths of the fundamental forces, the masses of particles, all of these emerge from the structure of the quantum fields that fill our universe. If the vacuum state of those fields changed, the laws of physics would change with it. Inside the expanding bubble of true vacuum, the rules would be different, not just different in some abstract mathematical sense, different in ways that would be utterly incompatible with the existence of atoms as we know them, of chemistry as we know it, of matter as we know it. The bubble would not destroy the universe in the way that a fire destroys a building. It would transform it into something that operates by entirely different rules, something in which the ingredients and structures of our current universe simply could not exist. There is no warning. There is no signal that travels ahead of the bubble wall, because the bubble wall itself travels at the speed of light, and nothing can outrun light. If a vacuum decay bubble formed anywhere in our observable universe, we would have no way to detect it coming. It would arrive without announcement and pass through everything instantaneously. One moment the universe is as it is. The next moment the physics has changed. Now breathe gently here, because this is a thought that could be frightening if you held it the wrong way. But try holding it differently. The probability of vacuum decay occurring in any given region of space, in any given span of time, is extraordinarily small. The universe has been around for 13.8 billion years, and no vacuum decay event has disrupted our region of space in all that time. The half-life of our vacuum state, if it is a false vacuum at all, appears to be vastly longer than the current age of the universe. Some calculations, depending on the measured values of the Higgs boson mass and the top quark mass, suggest that our universe may be in a state that is technically metastable, sitting in a very deep false vacuum with an extremely long decay time, but not technically unstable. Other calculations suggest it may be in the true vacuum already, in which case vacuum decay is not a concern at all. The honest answer is that we do not yet know with certainty whether our vacuum is stable, metastable, or unstable. The physics of the Higgs field, which is believed to be the field most directly relevant to the vacuum stability question, is still being measured and refined. The measurements needed to resolve the question require a precision that current particle physics experiments are approaching but have not yet fully achieved. But set aside the question of whether it will happen. Sit for a moment with the strangeness of the idea itself. The universe has rules. The rules are not written on stone somewhere, and then applied to matter. The rules are the behavior of the quantum fields that fill all of space, and those fields have an energy state, and that energy state could, in principle, change. The laws of physics are not eternal Platonic constants floating above the universe. They are properties of the universe, and like other properties of physical systems, they may be subject to change under the right conditions. This is one of the most quietly radical ideas in modern physics. The universe does not just exist within a set of laws. The universe, in some sense, is its laws, and its laws are a physical thing with an energy and a stability and a small but non-zero probability of being otherwise. There is a strange kind of awe in this, not fear, awe. The universe is not just old and large, it is contingent. The rules that allow stars to burn and atoms to bond and water to be water and life to be life are not the only possible rules. They are the rules that happen to apply in this particular configuration of quantum fields. And elsewhere, in some other vacuum, the rules are different. Somewhere in the mathematics of quantum field theory, there are valleys we have never seen, energy states we have never inhabited, physics we have never experienced and cannot imagine. The universe we know is one room in a much larger house, and we have not yet seen all the rooms. Let us drift now to something we have touched on before, but which deserves its own quiet time. The slow evaporation of black holes through Hawking radiation. We mentioned in the second part of our journey that black holes are not permanent, that Stephen Hawking showed in the 1970s that black holes slowly radiate energy and gradually lose mass. Let us sit with this idea more carefully now, because the full strangeness of it reveals something profound about the quantum nature of space and time. Near the event horizon of a black hole, the boundary beyond which nothing can escape, the quantum vacuum does something unusual. The constant flickering of virtual particle pairs that fills all of space takes on a particular character near this boundary. Occasionally, a pair of virtual particles appears near the horizon, and before they can annihilate each other, one of them falls inside the event horizon and the other escapes outward into space. The one that escapes becomes a real particle, carrying real energy. And because that energy has to come from somewhere, it comes from the black hole itself. The black hole loses a tiny, almost unimaginably small amount of mass with every particle that escapes. This outgoing radiation is Hawking radiation. And over time, across timescales that make the current age of the universe seem like a brief opening chord, it causes the black hole to shrink and eventually vanish. The timescales involved in black hole evaporation are worth dwelling on, not because they are useful to know, but because they stretch the imagination in a way that is itself a kind of meditation. A black hole with the mass of our Sun would take approximately 2 × 10 to the power of 67 years to fully evaporate. We have encountered this number before. But now, consider a supermassive black hole, the kind that sits at the center of a large galaxy, containing perhaps 10 billion times the mass of the Sun. Its evaporation time would be roughly 10 to the power of 97 years. That is a number so large that if you wrote out every digit, the list of digits would be far longer than the observable universe is wide, if each digit were written at atomic scale. The universe is currently 13.8 billion years old. That is roughly 10 to the power of 10 years. The evaporation time of a supermassive black hole is 10 to the power of 97 years. The ratio between those two numbers is 10 to the power of 87. If the current age of the universe were 1 second, the evaporation time of a supermassive black hole would be longer than 10 to the power of 79 years. These numbers do not fit in the mind. They can only be felt, the way you feel the depth of a dark sky, not by measuring it, but by letting your gaze go soft and allowing the darkness to be what it is. And yet even these black holes will eventually finish. The last supermassive black hole will radiate its final particle into a universe that has been dark for longer than any number we have encountered tonight. And when that last particle is radiated, the universe will be in a state that physics has not yet fully described. Every black hole gone, every star long extinguished, every white dwarf long since cooled to a black dwarf, every proton, if protons are not stable, perhaps long since decayed. Only the faintest imaginable background of radiation, stretching thinner and thinner as the universe continues to expand, and an extraordinary amount of time still ahead. Because the heat death, the true final stillness of maximum entropy, comes after even this. The universe after the last black hole evaporates is not yet at maximum entropy. It is still expanding. The radiation still has gradients, still has structure at the quantum level. Entropy is still, infinitely slowly, still increasing. The universe still has, in the most technical sense, somewhere to go. And it is in this extraordinary emptiness, in this vast, quiet dark after all the fires have gone out and all the black holes have evaporated, that quantum mechanics reveals one more layer of strangeness. In quantum mechanics, the vacuum is never completely inert. The fluctuations that produce virtual particle pairs, the flickering that gives rise to Hawking radiation, continue even in a universe that appears to contain nothing. And over timescales that are, even by the standards of this conversation, almost incomprehensibly long, these fluctuations can do something that seems impossible but follows directly from the mathematics. They can spontaneously produce configurations of matter and energy that have an extremely low probability of occurring but a non-zero one. And given enough time, a quantity of time that makes even the evaporation time of supermassive black holes look brief, even very low probability events will occur. What kind of configurations? In principle, any configuration that the laws of physics permit. A single photon appearing from the vacuum and then vanishing. A small cluster of particles briefly assembling and dissolving. And at the extreme end of this spectrum of unlikely events, over timescales so vast they require numbers with hundreds of digits just to write down the number of zeros, the vacuum could theoretically fluctuate into a configuration that assembles something structured. A rock, a planet, a galaxy. In principle, given enough time, a quantum fluctuation could assemble any configuration that the laws of physics allow, including ones that are large and complex. And here, the journey leads to one of the strangest philosophical puzzles in all of cosmology. It is called the Boltzmann brain. Ludwig Boltzmann was a 19th century Austrian physicist who laid much of the mathematical groundwork for our understanding of entropy and statistical mechanics. His ideas led, among other things, to an understanding of why the universe tends toward disorder. Any large collection of particles, any system with many possible configurations, will naturally tend to spend most of its time in the most probable configurations, which are the disordered ones, rather than in the rare ordered configurations. Order is improbable. Disorder is the default. But Boltzmann also recognized a disturbing implication of this thinking. If the universe is very old and very large, and if quantum fluctuations can produce ordered configurations from disorder, then eventually, given enough time, the vacuum will fluctuate into a state that contains something very particular, a brain. A fully formed, conscious brain, with memories and perceptions and the experience of existing, assembled from quantum noise, existing for a brief moment in the void, and then dissolving back into randomness. This is the Boltzmann brain, and the philosophical puzzle it poses is genuinely unsettling, not in a frightening way, but in a way that makes the foundations of reasoning feel a little less solid. If such brains are possible, and if the universe lasts long enough for them to occur, then there will be vastly more Boltzmann brains in the history of the universe than there are ordinary observers like us. Observers who grew up in a structured universe, embedded in biology, surrounded by other people and physical objects, and a consistent past. Because Boltzmann brains require only a single quantum fluctuation, while ordinary observers require a whole universe full of structure and history. If there are more Boltzmann brains than ordinary observers, then simple probabilistic reasoning might suggest that any given mind is more likely to be a Boltzmann brain than an ordinary observer, which would imply that your memories of having lived a life, of having grown up and learned things and experienced the world, might themselves be the product of a random fluctuation rather than a real history. The universe you seem to remember might not exist. You might be a momentary eddy of order in a maximally disordered cosmos, destined to dissolve back into nothing in the next instant. Now, take a breath, because this is a thought experiment, not a conclusion. Most physicists who take the Boltzmann brain seriously do not believe that you are one. Rather, the Boltzmann brain is used as a test for cosmological theories. If a theory predicts a universe that produces more Boltzmann brains than ordinary observers, most physicists regard that as evidence against the theory, a sign that something is wrong with its assumptions. A good theory of the universe should explain why ordinary observers like us, embedded in a structured world with a real past, are the typical kind of observer rather than the exception. The Boltzmann brain puzzle is less a genuine threat to your existence and more a philosophical tool for evaluating whether a cosmological scenario is consistent with the fact that we find ourselves in the kind of universe we do. But the strangeness of the puzzle is worth sitting with for a moment, the way you might sit with a very unusual piece of music, not trying to resolve it into something familiar, but just letting it be what it is. The idea that consciousness, the most intimate thing any of us has access to, could in principle be assembled by chance from the random behavior of quantum fields. The idea that the feeling of being a self might be thermodynamically possible, even in a universe that contains nothing else, is one of the most philosophically vertiginous ideas to emerge from serious physics. It is not comfortable, but it is genuine, and it is the kind of idea that appears only when you take the mathematics of quantum mechanics seriously across truly vast spans of time. There is one more quiet possibility to visit before we leave this strange quantum landscape, and it is, in some ways, the most extraordinary of all. In certain theories of quantum cosmology, particularly those related to the ideas of physicists like Alexander Vilenkin and André Linde, the quantum vacuum of our universe is not just capable of producing Boltzmann brains. It is, under the right conditions, capable of producing entire universes. The process is called quantum tunneling from nothing, or eternal inflation, depending on which framework you are working in. The basic idea is that the same quantum mechanical process that might allow a false vacuum to decay into a true vacuum, the tunneling through an energy barrier, could also, under certain conditions, allow a region of space to spontaneously develop into a new expanding universe, complete with its own Big Bang, its own physical laws determined by its particular vacuum state, and its own vast future of stars and galaxies and time. In the framework of eternal inflation, our universe is one bubble in a vast foam of universes, each one nucleated from a quantum fluctuation in a larger inflating space, each one governed by the particular vacuum state it settled into when it formed, each one unaware of and unable to communicate with the others. The space between the bubbles continues to inflate forever. The quantum fluctuations continue to seed new bubbles, and the result is a multiverse that is both eternal and ever-growing, generating new universes without end. This idea connects back, in a quiet way, to everything we have visited tonight. If new universes can nucleate from quantum fluctuations in an inflating background, then the ending of any particular universe is not the ending of everything. It is only the ending of one bubble. The background continues, new bubbles form, The process of cosmic creation goes on, in a space larger and stranger than any single universe can see, forever. Whether this is true is, of course, beyond our current ability to test. The other bubbles, if they exist, are by definition outside our observable universe. Their light can never reach us. Their history can never be read from our measurements. The multiverse is a prediction of certain well-developed physical theories, but it is a prediction that may be permanently beyond observational reach. This is one of the most contested questions in contemporary physics. The question of whether a theory that makes correct predictions within our observable universe, but whose broader implications lie outside it, can be considered scientific in the traditional sense. There is no easy answer to that question, and tonight is not the place to resolve it. Tonight we are only walking through the landscape of possibilities, pausing at each one to notice its shape and its strangeness and its particular kind of beauty. The quantum endings of the universe, vacuum decay and Hawking evaporation, and Boltzmann brains and nucleating universes, they are the most exotic flowers in this garden. They require the most careful mathematics to describe. They live the furthest from ordinary experience. They strain the intuitions we have built up from a lifetime of living in a world of middle-sized objects moving at middle-sized speeds. And yet, they follow. They follow from taking the physics we know, the quantum mechanics we have tested in thousands of experiments, seriously at the extreme edges of scale and time. They are not fantasies. They are the honest extrapolations of the deepest science we have, carried forward into the darkest and most distant regions of time and possibility. They are the universe being stranger than anyone expected, which is, if you think about it, one of the things the universe does best. Rest here for a moment in the strangeness. Let the image of empty space flickering with virtual particles, of black holes slowly breathing out their last light, of quantum fluctuations assembling brief moments of order in the deep dark, of new universes bubbling into existence from the foam of an eternal inflation. Let all of these images drift through your mind the way clouds drift across a dark sky. You do not need to hold any of them tightly. You do not need to resolve them into certainty. They are here for the same reason all the best questions are here, not to be answered tonight, but to be carried gently forward into sleep, where perhaps some deeper part of the mind will turn them over quietly and find in them whatever they are meant to yield. The universe is stranger than we need it to be. It is more generous with its mysteries than any one mind can fully receive. And that strangeness, that generosity, is itself a kind of gift. To live in a universe this interesting, this layered, this full of possibilities that reach down to the smallest scales and out to the furthest time scales, is an extraordinary thing. It is a thing worth noticing. It is a thing worth pausing here in the quiet to appreciate. In the final part of our journey tonight, we will rise back up from the quantum depths and return to the large-scale view. We will gather the threads of everything we have visited, heat death and the big rip and the big crunch and the cyclic cosmos and the quantum strangeness, and we will ask, very gently and very carefully, which of these endings the universe seems to prefer. We will look at what the evidence actually says, what the best measurements and the most careful science currently suggests about where all of this is heading. And then we will let the journey come to rest, slowly and softly, the way all good journeys end, not with a dramatic conclusion, but with a quiet arrival, a setting down, a stillness that feels, after all that distance traveled, like exactly the right place to be. We have traveled a long way tonight. We have walked through the slow cooling of heat death, the unbinding cascade of the big rip, the collapsing symmetry of the big crunch, the breathing rhythm of the cyclic cosmos, and the deep quantum strangeness of vacuum decay and evaporating black holes and fluctuating universes. We have visited 5 different kinds of ending, 5 different answers to the question of how everything finally concludes. And now, In this last quiet passage of our journey, we are going to ask the question that has been waiting patiently underneath all the others. What does the evidence actually say? When cosmologists set aside the beauty of the theories and look at the measurements, at the real data gathered by real instruments pointed at the real sky, which ending does the universe seem to be moving toward? This is not a simple question, but it has a shape, and the shape of it, when you hold it gently, is itself something worth resting inside for a while. Let us return to each theory in turn, one last time, and listen to what the evidence says about it. The Big Crunch was, for most of the 20th century, a genuine contender. The question of whether the universe would expand forever or eventually collapse depended on the density of matter, and for decades that density was uncertain enough that collapse remained possible. But when the accelerating expansion of the universe was discovered in 1998, the Big Crunch scenario became much harder to sustain. For the universe to collapse, the expansion would need to reverse. For the expansion to reverse, gravity would need to overcome whatever is driving the acceleration. And what is driving the acceleration is dark energy, which currently makes up roughly 68% of the total energy content of the universe. The matter that gravity works with, the visible matter and the dark matter combined, makes up only about 32%. Gravity is already the minority partner. It is already losing to dark energy. For it to turn the expansion around would require either that dark energy weakens dramatically over time, for which we currently have no evidence, or that our understanding of dark energy is fundamentally wrong in ways we have not yet detected. The Big Crunch is not impossible, but it requires the universe to behave in ways that currently available data does not support. Most cosmologists today regard it as unlikely. The Big Rip is a more delicate case. The Big Rip requires dark energy to be a form of phantom energy, a type of energy whose density increases as the universe expands, rather than staying constant. Whether dark energy is constant or changing is one of the central questions of modern observational cosmology. The data currently available, from the Planck satellite's mapping of the cosmic microwave background, from large surveys of galaxy positions and distances, from measurements of supernovae across cosmic distances, all of this data is consistent with dark energy being a cosmological constant, a fixed and unchanging energy density. The measurements are precise enough to say that if dark energy is changing, it is changing very slowly, within a range that current instruments can only barely begin to probe. The Big Rip is not ruled out. But it requires dark energy to be something other than what it currently appears to be, and the current appearance is of constancy. The Big Rip remains a real possibility, but it is not the favored outcome given what we can measure today. The cyclic models, the Big Bounce and conformal cyclic cosmology, and the ekpyrotic scenario face a different kind of challenge. They are not primarily ruled out by direct evidence. They are challenged by the difficulty of making predictions that can be clearly tested. The Big Bounce requires a quantum theory of gravity that we do not yet have in a complete and agreed-upon form. Conformal cyclic cosmology predicts subtle patterns in the cosmic microwave background that remain deeply controversial. The ekpyrotic model depends on structures in higher dimensions that we cannot directly observe. These theories are alive and active in the research literature, but they have not yet produced a clean, confirmed prediction that distinguishes them from the simpler scenarios. Science requires contact between theory and observation, and these theories have not yet fully made that contact. They remain beautiful, they remain possible, but they are waiting for evidence in a way that the heat death scenario is not. And that brings us to heat death. The heat death scenario, the slow and patient cooling of the universe toward maximum entropy, does not require anything exotic. It does not require dark energy to change. It does not require gravity to overcome acceleration. It does not require quantum gravity or extra dimensions or tunneling between vacuum states. It requires only two things: both of which are currently well supported by observation. The first is that the second law of thermodynamics continues to hold. Entropy always increases. This law has never been observed to be violated in any physical system anywhere in the universe, and there is no theoretical reason to expect it to ever be violated. The second is that the universe continues to expand, driven by dark energy that remains roughly constant. The current measurements of the expansion rate, of the geometry of space, of the behavior of dark energy, all support this picture of a universe that will expand forever, growing larger and emptier and colder, until nothing new can happen and everything settles into permanent quiet stillness. The geometry of space itself is one of the most important measurements in this story. Space can be curved in different ways. It can be positively curved, like the surface of a sphere, in which case the universe is finite in volume and its geometry points toward eventual collapse. It can be negatively curved, like the surface of a saddle, in which case it is infinite and will expand forever. Or it can be flat, in which case it is also infinite and will also expand forever. The measurements of the cosmic microwave background, the most precise map we have of the early universe, tell us that space is flat, or very nearly flat, to within the limits of our current ability to measure. A flat universe is a universe that expands forever. A universe that expands forever, subject to the second law of thermodynamics and the constant gentle push of dark energy, tends toward heat death. This is why most working cosmologists, when pressed for their best current guess about the fate of the universe, point toward heat death. Not because it is certain, not because the question is closed, but because it is the scenario that requires the fewest additional assumptions, that follows most directly from the laws we know and the measurements we have made, that demands no dramatic change in the behavior of the forces we observe. Heat death is the conservative conclusion, the quiet one, the one that emerges when you take what is already known and follow it forward as honestly as you can. But the universe has surprised us before. This is not a small caveat. This is one of the most important things that the history of science teaches, that the universe is under no obligation to behave the way we expect, and that our current best understanding has been overturned, sometimes completely, by new observations. The accelerating expansion itself was one of those surprises. Before 1998, almost no one expected it. The discovery came from careful measurement, from following the data where it led, even when it led somewhere unexpected, and it transformed our understanding of the cosmos completely. Dark energy, the force that now dominates our best model of the universe's fate, was not part of any mainstream cosmological scenario before that discovery. It arrived uninvited and changed everything. There may be other surprises waiting. There may be properties of dark energy that our current instruments are too crude to detect. Slow variations that will only become apparent with decades more of careful observation. There may be aspects of quantum gravity, the theory that will one day reconcile quantum mechanics with general relativity, that change the story in ways we cannot yet anticipate. There may be physics beyond the standard model, new particles or fields or interactions that play a role in the long future of the cosmos. The universe is not obligated to have finished revealing itself to us. And the history of cosmology is a history of radical revision, of cherished certainties giving way to stranger and deeper truths. The right relationship to hold with the question of the universe's ending is not certainty. It is careful attention. It is the willingness to follow the evidence while holding the conclusions lightly. It is the posture of a good scientist and, in a quieter way, the posture of a good listener, open to being surprised, willing to update, curious about what comes next. The universe will tell us more if we keep listening carefully, and what it tells us may be different from what we currently expect. And here, gently, is the thought that has been waiting underneath everything we have discussed tonight. All of these endings, Heat death and the big rip and the big crunch and the big bounce and vacuum decay and every strange quantum possibility, all of them share one feature. They are so distant in time that they barely belong to the same conversation as the present moment. The heat death, the most likely scenario, will not arrive for timescales measured in numbers with 80 or 90 or 100 digits. Even the nearest and most dramatic of the exotic endings, vacuum decay, has a half-life for our vacuum state that is almost certainly longer than the current age of the universe by an enormous margin. These endings are not waiting for us around any corner we can see. They are not waiting for us around any corner our great-grandchildren's great-grandchildren can see, or any corner reachable in any number of human generations that the imagination can hold. What this means, held quietly, is that the ending of the universe is so far away that it almost ceases to be an ending in any emotionally meaningful sense. It is a feature of a scale of time so vast that it does not connect to any experience we have of loss or change or the passing of things. We grieve the endings that are close. We feel the weight of the things that leave within a human lifetime, within a human history. The ending of the universe does not belong to that category. It belongs to a scale so different from the scale of human life that it is, in a very real sense, not part of our story at all. And what remains, when the ending is lifted away to that impossible distance, is only the present, only this, the universe as it is right now, in this moment, in this long, bright middle of its life, full of burning stars and drifting galaxies and complex chemistry and living things, and the particular quiet awareness of a person resting in the dark, wondering about it all. There is a gift in the scale of cosmic time. It does not make the present moment smaller, it makes it more itself. You are not on your way to the heat death of the universe. You are in the universe's youth, its long and radiant middle age, the era in which complexity exists, in which stars still have fuel, in which planets hold water, in which the conditions for life and thought and feeling are still in place. The universe is not old in the way that matters to you. The universe is still very much alive, and you are part of that aliveness. The atoms that make up your body were forged in the cores of stars that lived and died before the Earth existed. You are made of stellar remnants. You are the universe becoming aware of itself in one small and temporary way, the cosmos folding back on itself to look at its own face. The questioning you have done tonight, this gentle wondering about endings and timescales and the behavior of dark energy, is itself a feature of the universe, a process that could only occur because the universe is currently in the kind of state that allows for curiosity, for consciousness, for the particular experience of lying in the dark and thinking about very large things. That experience is not a small thing. It is, in a very real sense, what the universe is doing right now, in the neighborhood of this planet, in this quiet hour. It is looking at itself through your eyes. It is asking itself questions through your mind. It is noticing its own strangeness and beauty through your noticing of it. Let that settle. The universe gave you the capacity to wonder about its ending. That is a remarkable thing. More remarkable, perhaps, than any of the endings we have visited tonight. Because the endings, all of them, are things that will happen to matter and energy across vast timescales that no mind will be present to observe. But this moment, this wondering, is happening now. It is real in a way that no distant future event can yet be real. And now, as this journey comes toward its rest, let the thoughts grow quieter. Let the galaxies drift. Let the stars slowly cool in the distances. Let the black holes take their trillions of years, patient and unhurried. Let dark energy do what dark energy does, constant or shifting, moving at its own pace through timescales too long for urgency. Let the quantum vacuum flicker with its borrowed energies, its brief particles appearing and dissolving. Let the universe move toward whatever ending it is moving toward, gently, at its own speed, without needing anything from you tonight. You have traveled far in this quiet hour. You have visited the slow cooling of all the fires. You have felt the universe unravel thread by thread in the big rip. You have watched it fall back into itself and perhaps begin again. You have stood at the edge of the quantum world and heard the sound of empty space. You have asked which ending is most likely and received the most honest answer science can currently give. And now the journey comes home. Feel your body where it rests. The weight of it, the warmth of it, the slow rise and fall of your chest. You are a living thing in a living universe. The stars outside are still burning. The Milky Way is still turning its slow wheel above you. Hundreds of billions of stars keeping their patient orbits. The same stars that looked down over the first human fires. The same stars that will still be there long after any building standing now has dissolved into soil. The universe is still full of light. It will be full of light for a very long time. Your body is heavy and warm. Your breath is slow. There is nothing required of you now. No understanding to reach. No question to resolve. Only the simple, ancient comfort of a small creature resting in the dark beneath an enormous and still burning sky. The heat death is 10 to the power of 100 years away. You have tonight. Let your eyes stay closed. Let the galaxies drift where they will. Let the questions you carried here tonight rest beside you like small stones gathered on a walk, interesting and solid and no longer needing to be held. The universe knows where it is going. It has time. And you have this breath, and the next one, and the one after that, slow and easy, carrying you down. Wherever you are in the world tonight, whatever hour glows softly somewhere near you, you have spent this time in good company. You have thought about the largest things. You have held them gently. And now you can let them go. Sleep well. The stars are keeping watch.